Our next speaker is Alin Tomescu. I hope I have pronounced your name right. Who's currently a postdoctoral researcher at VMware Research. Previously, he has obtained a PhD from MIT, focusing on public key distribution and threshold cryptosystems. And the talk that he's going to present today is titled "Towards Scalable Threshold Cryptosystems." The stage is yours, Alin.
Thank you. Thank you so much for the introduction, Fatima. I'm not sure if I'm pronouncing your name correctly. And Fateme. Thank you for the invitation, Fateme. Yes. And thank you, Aniket, as well, for the invitation. It's a pleasure to be here. So my name's Alin, and I like three things: applied cryptography, motorcycles, and managing my academic bibliography using CK. So you can see an example of that in the chat for how I was able to come up with that quick citation for Aniket's work. So today I'm going to be talking about our work on scaling threshold cryptosystems. This is joint work with my high school students, Robert and Yiming, who I had the pleasure of mentoring while I was at MIT, and who are now MIT students themselves, with my collaborators at VMware Research and with my advisor, Srini Devaras at MIT. And by the way, this presentation will be very similar to Mary's in the sense that we're also going to be talking about DKGs, but we're also going to be talking about threshold signatures. So it's a two-part presentation, and I'll start by sort of motivating the problem. So we're all familiar with signature schemes. You have a device that has a secret key and issues signatures on messages by calling an API called sign, which takes the message, the secret key, and outputs the signature. And then verifiers can use an API called verify, which takes the signature, the message, and the public key associated with the secret key to verify the signature. And in these schemes, what you want is you really want to protect the secret key, because otherwise an attacker can issue signatures on your behalf. And we all know that signature schemes are used in things like WhatsApp. So when you use WhatsApp on your phone, you actually sign the messages you send to your friends, so your friends know they came from you. So it's very important to protect these secret keys. And obviously, we don't want the attackers to get their hands on them. And one way to do this is via threshold signature schemes, which were originally introduced by Desmet in '87. And the idea here is that I'm going to take the secret key and split it amongst a bunch of devices, say 5, such that any 3 out of the 5 devices can reconstruct. So maybe the first 3 or the last 3 or any other 3, but no less than 3 can. And to produce a signature, now each device signs independently, so takes their share of the secret key and the message and produces what we call a signature share. So let's say the 3rd device does the same and the 5th device does the same. Then you can aggregate these signatures via an aggregate API, and which actually gives you the signature sigma as if you produced it using the secret key, which nobody had. So it's kind of magical, but these things exist. And then a verifier can verify the signature as before. The verifier has the public key corresponding to the secret key, which nobody knows, and can still verify the signature. And even better, the verifier doesn't even have to know that this is a threshold scheme. From his perspective, he has no idea that he's dealing with a threshold scheme. The nice thing about this is that if you do this T out of N sharing, so N is 5 here and T is 3, then you can tolerate up to T-1 compromises. So if I compromise 2 devices, I still can get the secret key. I need to compromise 3 devices. So it gives you more resiliency, but it does assume uncorrelated vulnerabilities or failures in the devices. And that's a big question and ground for important future work to be done. So why would you want to use these threshold signatures? I think they're really a key decentralized crypto primitive. So imagine your Bitcoin wallet that has a secret key and you want to protect it to not lose your coins. You might want to split it amongst a bunch of trusted parties in a secret sharing manner, as explained before. And this way, if somebody compromises only T-1 of these trusted parties, your secret key stays secure. And the larger the threshold T is, the better security you get. They're used to scale consensus protocols or to build random beacons, as Mary described, or for even very naive voting protocol. And in these applications, you actually need a large threshold T and a large number of participants N, because let's say you're voting in America, N is 300 million, T is 150 million. And this kind of motivates our work. We asked the question of, can we scale threshold signatures to ridiculously large thresholds T? So it's kind of something that we were interested in around 2017 or so. And as a bonus, can we get efficiency at small scales too? And to answer this question, I'm going to break it up into 2 parts. So the first part is, how do we actually split the secret key amongst these 5 devices? So I have 5 devices and they want to bootstrap a threshold signature scheme so they can issue signatures. How can they do that at scale? Because I actually don't have 5 devices, I have 5 million. So it better be scalable. And one answer here is, well, use a verifiable secret sharing protocol where you have a dealer who has the secret key and splits it to these players. But the problem with this verifiable secret sharing protocol is that you have a dealer and he has the secret key. Therefore, you don't have a threshold signature scheme because the dealer knows the secret key. So it's not the case that that only a coalition of T players can sign. The dealer can also sign. So that's no good. But what people in the past have shown is that you can build a distributed key generation protocol from a bunch of parallel executions of verifiable secret sharing protocols. And in these DKG protocols, these 5 players are able to generate these individual secret key shares for each player without actually learning the secret key. So at the end of this DKG protocol, every player I gets SKI, but no player learns the secret key SK. And in the purpose of this talk, we're going to focus on scaling VSS protocols, because once you scale VSS, you can scale DKG. And feel free to ask me at the end about how to scale DKG. And the second challenge is, now I have this threshold scheme. People are producing these signature shares. I have T signature shares, and I need to aggregate them into one threshold signature. How can I do that at scale? One answer is use Lagrange interpolation, because most of these schemes use polynomial interpolation. But unfortunately, most implementations of threshold schemes seem to use a really naive Lagrange interpolation scheme. And we show that faster algorithms exist and should be used in practice because they make a lot of sense, especially at large scales. And I'll begin by talking about VSS, and then we'll go into the aggregation part. So let's talk about Shamir's secret sharing, originally introduced in '79. The idea here is that you have this dealer that I mentioned earlier. He has the secret key and wants to split it to n participants such that any T of them can reconstruct the secret key. And the way he does that is by picking a random polynomial phi, where phi of 0 is the secret key. And this polynomial phi has degree T minus 1. And then he gives each player I its share of the secret key SKI as phi of I. That's how SKI is defined. And now when you want to reconstruct, you take any subset of 3 shares. So you take phi 1, phi 2, and phi 5, let's say, and you do Lagrange interpolation, which I'll talk about later, and you can reconstruct the secret key. And it doesn't even matter which shares you get. As long as you have 3, Lagrange interpolation guarantees to you that you can reconstruct the same secret. But the problem is that the dealer could be malicious. So he might give the players completely invalid shares. He might give this guy the share 5 rather than phi of 1, let's say. And also the players are malicious. So they might give this reconstructor bad shares. And then the reconstructor will reconstruct different secret keys based on which players were malicious. So that's no good. We want to always reconstruct the same secret key. And we always want the players to be able to reconstruct the secret key SK. So players need to ensure that their shares are correct. And there's a long line of work on this called verifiable secret sharing that prevents these types of attacks. So in verifiable secret sharing, what you do is, as before, you have your dealer, you give each player their share of the polynomial, but you now commit to this polynomial using a polynomial commitment scheme, which is a black box that we'll go into a bit later. And you get this commitment C of the polynomial phi. And now you broadcast this commitment C to all of the players. And broadcast is really important here. This was kind of touched upon in the questions after Mary's talk. It's very important that everybody agree on the C, all the players. So ask me at the end if that doesn't make sense. And you'll also give the polynomial shares to everybody. And now you also give them a proof that a proof phi of pi I, that phi of I is indeed the correct evaluation for the polynomial phi committed in the commitment C. And now during reconstruction, if a player wants to give a bad share, well, the reconstructor can verify that share with the proof and the commitment, assuming the reconstructor also gets the commitment. So the reconstructor has access to this broadcast channel as well. So now you deal with malicious dealer, because dealers can give bad shares anymore because they have to prove the shares against the broadcasted commitment, and you deal with malicious players. And one thing I'm ignoring here is the complaint phase, but Mary already kind of told you a lot about that. There's a complaint phase in VSS protocols as well, inherited by DKG protocols usually. But what I really want to talk about in this talk is the scalability challenge, which is that these commitments are either big or slow. So big means the commitment might be order t-sized, for example, if you use Peterson commitments. And slow might mean that the proofs take a long time to compute if you use Kate, Zaverucha, Goldberg, or KZG commitments. So KZG commitments are actually small, but the proofs before our work took a lot of time to compute. And real quickly, since this talk is focused on KZG, the way a KZG commitment works is you have a trapdoor tau, you evaluate phi at this trapdoor tau that nobody knows tau, and you raise G to phi of tau. And the question is, how can you do this when nobody knows tau? And the answer is kind of, well, you have this common reference string, G to the tau to the I, for a bunch of different i's up to t. And given these common reference strings, you can actually compute this. So we won't go into too many details about this, but I'm happy to talk about it at the end. And you have Aniket here, who can tell you much more about it than I can. So the problem with we're going to focus now on VSS with KZG, which is called EVSS, originally introduced by this paper by Kate et al. And if you look at KZG-based VSS, from the dealer's perspective, dealing doesn't scale very well. So on the x-axis, we have the total number of players, the n, and on the y-axis, we have the time in seconds to deal. And the dealing time grows with the time to compute all of the proofs. So it's order nt time. And this is, fine for small scales, a bit expensive for larger scales, and kind of prohibitive for ridiculously large scales. And what we do is we drastically reduce this time by reducing the time to compute the proofs in the KZG polynomial commitment scheme. So we reduce time from a year to tens of minutes, from hours to a minute, and from a minute to seconds. And that's sort of the first half of this talk. And the key ingredient we use to reduce the proving time in the KZG scheme is a polynomial multipoint evaluation, which is a classic technique from 1972 is the earliest reference I could find. And here, the idea is that I have the polynomial phi that I mentioned earlier, and let's say I want to compute proofs for phi of 1, phi of 2, phi of 3, and phi of 4. I'll take phi, I'll build this accumulator polynomial, which has a root at every evaluation point, and I'll divide phi by it. And I will get a quotient and a remainder, as I do when I divide two polynomials. And now I'm going to recurse. I'm going to take this remainder and divide it by the left half of this accumulator, and take the same remainder and divide it by the right half. And I now can repeat recursively. I have another division here and another division here. I get some quotient remainder here, some quotient remainder here. Again, I take this remainder, divide by left, divide by right. I take this remainder, divide by left, divide by right, all the way until the remainder is a constant term. And actually, the constant term that I get are the evaluations of the polynomials itself. And I won't go into details about why this is the case, but you can see real quickly that phi modulo this, and modulo this is just phi of 1, because phi modulo x minus 1 is phi of 1. That's kind of the intuition. And what we do next to obtain proofs is, well, before that, we can compute this in order n log t time if you pick these points 1, 2, 3, 4 carefully to be roots of unity. And next, to actually obtain proofs for the KZG scheme, we are going to look at this evaluation tree and ignore the remainders. So we're just left with the quotients. And we're going to commit to the quotients using the KZG polynomial commitment scheme. And everything is constant size now in every node. And we call this an authenticated multipoint evaluation tree, or an AMT. And I can, after I compute the tree, I can commit to it in order n log t time. And a proof will now be a path of these quotients. So if I want to prove phi of 3, well, then I give you all of the quotients along the path to 3. And everything is constant size. So the proof is order log t sized, because this tree has log t height. We argue in the paper why that's the case. Now, you might notice that this is a trade-off after all. We have slightly larger proofs because KZG proofs are constant sized. We have log size proofs, but our proofs are much faster to compute. So that kind of finishes the first part of the talk. And what we showed you so far is how to sort of do verifiable secret sharing at a larger scale by reducing the time to deal from a year to tens of minutes. And next, I claim that you can use this scalable VSS to build a scalable DKG. For the details, please see my paper, or we can talk about it at the end. The next challenge is we have to scale aggregation. So again, I have a bunch of signature shares from T players, and I want to build a single threshold signature by aggregating them into one. And how do I do this? And like I said before, the problem is you might be tempted to use slow Lagrange interpolation. As far as we could tell, all implementations do this. But this will not scale very well. So if you take the BLS signature scheme, and you, on the x-axis, I have the total number of signers. So the threshold is this divided by 2. And on the y-axis, I have the time to aggregate T BLS signature shares into one BLS threshold signature. Then the scaling time scales quadratically with the threshold T. So you get very nice performance at small scales, reasonable performance at large scales, and very bad performance at ridiculously large scales. And before we're going to talk how to improve this, let me give you a hunch of why this time is order t squared. So the idea is that when you aggregate a threshold signature, you reinterpolate the secret key in the exponent, roughly speaking. But what you're doing is you take the secret key shares of every player who's helping you aggregate. So you have a bunch of players in the set P, and you multiply its share by this Lagrange coefficient. So you have T of these Lagrange coefficients that you want to compute. And each Lagrange coefficient looks like this. It's a numerator divided by a denominator. Now, the numerators, I have to compute T different numerators for the T different coefficients. And I have this common product, which I can compute in order T time. And then I can do T different divisions. So I can compute all of the T numerators in order T time. So that's good. But for the denominator, I kind of get into trouble because at first glance, it's very unclear how to compute all T different denominators in less than order T squared time. This is because I is different for every denominator. And what previous people have shown is that you can actually solve this problem using polynomial multipoint evaluation. And our work merely observes that you can apply this to the BLS threshold signature scheme, as well as any other threshold crypto systems. And I won't go into details about how, but I will show you the performance gains you get. So at large scales, we go from tens of hours to tens of seconds. Well, this is ridiculously large scale. At large scale, you go from 2 minutes to 1.5 seconds. And even at small scales, you get a significant reduction in the aggregation time. So we're very happy with both improvements in the VSS time and the aggregation time. And I think this kind of concludes my work, my presentation, in the sense that we showed how to aggregate threshold signatures via faster interpolation. We shaved off an order T factor and replaced it with a log squared T factor. And then we showed how to scale VSS via AMT proofs by shaving off this T factor, replacing it with a log T factor, which makes a huge difference. And in general, this AMT technique is, I think, of independent interest because it can be used for things like vector commitments. And you might object and say 1 million is unreasonably large. Who's ever going to use that? And first, I ask that you keep an open mind. And second, we are faster at small scales too. It's not that hopeless. The future work, well, I kind of ignored complaint broadcasting, which Mary touched upon in her presentation. So it's very important to address that. So our experiments don't really address the overhead. And remember, I mentioned this broadcast channel in the VSS protocol, which again came up in Mary's talk. It's very important to scale this as well. And that's grounds for future work. And our code is available online in this GitHub repository. And that being said, do I have extra time, Fateme?
Yes, please. We are early. We started early, so yes. Perfect. Because I do want to talk about something else. So subsequent to our work, there was a very cool technique by Dankrat Feist and Dmitry Kovatovich on computing KZG proofs. So what they show is they give this beautiful order n log n time algorithm for computing all constant-sized KZG proofs. And in contrast, what we gave was order n log t time algorithm for computing log t-sized AMT proofs. They're not really KZG proofs, since they're log t-sized. So this kind of raises the question, well, if you implemented VSS using this technique for computing all KZG proofs fast, how would that compare to AMT VSS? And let's kind of explore that. So the first observation is that FK VSS dealing will be slower, as much as 10x slower, let's say. This is because when you compute proofs using the FK technique, you have to do FFTs, and FFTs can't leverage multi-exponentiations as well as AMTs can. That's kind of the intuition behind
this gap. So dealing is slower, but on the other hand, because proofs are smaller, FK produces constant sized KZG proofs, FK proofs are faster to verify, whereas AMT proofs take order log T time to verify. And in that sense, the reconstruction phase of the VSS protocol, which I didn't talk about before, will be faster. And for VSS reconstruction, you can think of two things. You have a best case where the reconstructor gets shares and everything is valid. And you have a worst case where the reconstructor gets n shares, but n minus t of them are invalid. So he has to find t valid shares. And here on the y-axis, I have the log of the threshold t being used in the VSS protocol. And here on the y-axis, I have time in seconds to reconstruct. And what we notice is that, well, for example, FK-VSS in the best case is much faster than AMT in the best case during reconstruction. And this has to do with the fact that an AMT proof takes log T time to verify, whereas a KZG proof takes order 1 time to verify. And in the worst case, AMT proofs are quite slow, because you have to verify much more of them. And part of this big gap here is we didn't leverage multi-pairings in our implementation. So this line could be a bit shorter if we're careful. And I also want to say that the FK-VSS best case and the AMT-VSS best case could be actually made the same if the VSS protocol were changed for the best case. Like you could do best case reconstruction much faster without verifying proofs if you change the protocol. So these two lines could be the same. But in the end, FK-VSS reconstruction will be faster, since at the end of the day, you're not going to be in the best case or worst case. You're going to be somewhere in between, and FK will likely perform better. Now, that begs the question, how does the end-to-end time compare? So you have dealing and reconstruction. And when you look at the end-to-end time, well, FK-VSS is faster in the worst case, but slower in the best case. So again, I think FK-VSS is the answer, because in reality, you'll be somewhere in between. And in terms of the speed up, if you look at the FK worst case speed up for the end-to-end time, you know, it tends to be around 2x over AMT. And if you look at the AMT speed up in the best case, it's above 2x. And another thing to point out here is that FK-VSS communication will be smaller than AMT-VSS, because KZG proofs are smaller than AMT proofs. So that'll also give you an additional speed up. And also, we did not account for complaint phase overhead, which has its own extra communication. So FK gains points there too, and extra proof verification. So again, FK gains points. So this is again grounds for really interesting future work. And with that being said, I think this concludes my presentation. And I have 2 blog posts on this paper with excellent GIFs and memes. So please go on these URLs and check them out. And I would be happy to take questions. Thank you so much.
Thank you, Alin.
Thank you.
Any questions? Or is everyone too tired?
So, Alin, thanks a lot for actually bringing the points regarding the FICE and Dankat scheme. It's good to see that you indeed did the comparison and saw it. I think it will depend upon the communication scenarios, right? There will be, if the communication is the bottleneck, then probably one thing will be better than other. But generally, typically in the cloud setting, I think you will start seeing that the communication is much faster and cheaper, so could play a role towards the constant side, the more communication not coming in picture at all, right? But if the communication is a challenge in some scenario where it's slow because of the large sizes, that there the things could play out.
Yeah, so I expect the log T factor incurred by AMT to negatively impact performance in many settings, I would say. But that being said, AMT dealing can be much faster. Is much faster. So, it would be cool to implement and see, especially with the complaint phase, right? Which we don't account for. Yeah.
Also, I have to check that for that. I did not check. So it's possible to do the pre-computation for sure, as I mentioned on the tweet. That you can also do that for AMT. Nice. I haven't yet checked that for the FICE and Cryptography scheme, if that can be done, but could be interesting.
Well, yeah. By the way, I should also mention that we have implemented this technique. So it's in the GitHub repo I mentioned above on its own branch. And these numbers can be reproduced if you want to take a look. Yeah.
There's also a question in the chat. In practical cryptographic applications such as random beacons or TSS, do we see more dealing operations or more reconstructions? For random beacons, I think there will be both.
Yeah, I think Aditya is asking about random beacons that are based on VSS and random beacons that are based on TSS, or maybe a combination of the two. You know, obviously, if you have a random beacon based on VSS, every output is a VSS reconstruction, so you care about dealing and reconstruction. But if you have a random beacon based on TSS, then you're going to bootstrap it using a DKG, so you care about the DKG bootstrapping time. So Aditya, I'm not sure how to answer your question beyond without knowing the exact random beacon design. If you want to clarify further.
I wanted to ask if in general cryptographic applications, do we see more dealings happening or more reconstructions happening? That was my question. So if we know that in our protocol, most of the time we'll be reconstructing rather than dealing, we might want to use one of your techniques. And if we know that we are going to be having equal proportions of dealing and reconstruction, we may want to optimize for that.
Right. So if you think about DKG protocols, they use more dealings than reconstruction. So in a DKG protocol, you have n dealings and maybe one reconstruction at the end, or maybe not even a reconstruction because you use it for a threshold signature scheme. Well, a reconstruction in the exponent in that case. But I think I don't want to claim anything about this because it's there's so many cryptographic protocols out there. I really don't know what to say.
No, even
yeah, I like the question, but I don't know how to answer it.
Even if we use a DKG I assume is a setup for something else.
Yes.
So
right.
There may be those factors as well. But yeah, just my comment. Sorry.
Mm-hmm. Right. Yeah. By the way, another sort of thing that I didn't touch upon was that our protocols require these public parameters, these G to the tau to the I's. So they require a trusted setup, and you kind of have a chicken and an egg problem. You're trying to do a DKG, but you need another sort of DKG protocol to compute this G to the tau to the I's. And that's kind of unappealing in some sense, but from a theoretical standpoint, at least. But from a practical standpoint, there's all of these public parameters online already that have been generated from trusted setup ceremonies that you can just pick up and run our protocols with. So from a practical perspective, I think it's not necessarily as bad. Yeah, so that's something I wanted to mention.
I also had a question. My name is Georgios. So that's a really interesting topic. My question is about the difference in the other protocol that you mentioned, the subsequent work. There was something really interesting, which is that they managed to avoid having the T factor completely out of the results. And I was wondering if you have any interest, like any intuitive explanation of how this happened with their algorithm at hand.
The intuitive explanation is that the FFT that they compute is of size n. So that's where the n log n factor comes from the FFT of size n. In our case, the log t factor has to do with the degree of the polynomial. When you compute this multi-point evaluation tree, at some point you bottom out very fast. It turns out you bottom out after log t levels. We have an explanation in the paper for why that's the case. Does that answer your question?
Yeah. Thank you very much. I mean, I'll read them through, so I'll also see it in practice.
Another thing that might be worth mentioning is that our AMT technique actually generalizes to any set of points, not just roots of unity. So if you want to do any set of points, this log t turns into a log squared t. Whereas, as far as I can tell, the FK technique is not as generalizable. It needs roots of unity or some other points that are that have roots of unity in them somehow, but they don't generalize to arbitrary points. So if you want to compute proofs for arbitrary points, it still seems like AMT is the best thing you can do.
So your AMT technique, somehow you managed to get log t and not log squared t, even though you don't have all roots of unity, right? Are these t's roots of unity or nth roots of unity?
Oh no, I have all actually. So yeah, I do have all t roots of unity. Let me just go to the slide, although I guess the slide doesn't make that clear. So here you see, I would actually need to have all n roots of unity here, because when I split this accumulator into halves, when I have all n roots of unity, these accumulators have a very nice special form when I split them into half. And that allows me to get a faster division than if these accumulators didn't have that form. And it's very important that I have all n roots of unity.
So you're still powers of 2 roots of unity, just like the FFT.
Yes, if I want to do n log t time to compute the multipoint evaluation tree, I need roots of unity. But if I'm willing to do n log squared t, I can do anything here. I don't need roots of unity.
Whatever, just saying that you need, like, so t is a power of 2, just like n is for the FFT.
N, this is n, it's not t here. The size of this is n. I'm computing n proofs, and the polynomial has degree t.
Okay.
Yeah, it's a bit strange, perhaps, I realize that. But yeah, we don't have any restriction on the degree t of the polynomial, but the number of points n has to be a power of 2, so you can get roots of unity. And you can see this very clearly in our code base, where our benchmarks we usually pick them so n is a power of 2, so we can do this very fast. I think there's something you want to ask. Did I fully answer your question?
Yes, yeah, I think that's right.
Oh, okay, cool.
There is another question in the chat. What happens when it's not a power of 2?
When it's not a power of 2, you can pad. That's one answer. You can just add the remaining evaluation points and just ignore the proofs for those. So you can still compute the AMT tree. It's just you're doing unnecessary work, but you can prune a lot of that unnecessary work if you do it carefully. So our code base takes care of non-powers of 2 too. So you can look at our code base exactly how we do that, how we avoid doing the extra work. There's probably clever things you could do for non-powers of 2. You could pick your field size to be a certain field size that admits roots of unity for non-powers of 2 probably. But we haven't explored that. So in principle, it works. You're wasting some computation, but there's ways to deal with that. Yeah.
Okay, if there are no other questions, thanks again for the interesting talk.
Thank you.